Okay, thanks very much, Irene. And thanks to the conference organizers for putting together what's been a great week and inviting me to speak here this morning. So, I'm going to pick up on the same of the IMBeR Grand Challenges that Laurent spoke to us about on Tuesday, and that's Grand Challenge 2. So the aim of this is to improve scenarios, predictions, and projections of future ocean-human systems at multiple scales. And Laurent focused on one part of the sentence, and I'm going to focus on the ocean-human systems at multiple scales part of the challenge. And I'm going to try to talk about a number of things very quickly, but I want to make sure I get two main points across. One of them is that the size spectrum perspective is awesome, and you should all love it. And the other one is that we need more direct integration of humans into global models. So first, why global? I know many people are skeptical of global approaches, and you should be skeptical, because everything that's important happens locally. It doesn't happen globally. The global is the sum of many local things, and if you've tried to work on understanding local process, you know that those are hard. So scaling things up to the global processes should be even harder. And it's definitely a difficult thing to do, but I also think that it's essential. I think it's essential because it provides a context for the local changes that are happening. It fills gaps where we're lacking local information, and I think this is important for something that Ingrid talked about the other day, which is the ambiguity problem, that people have a hard time taking action on things where they don't see the whole picture. It can also help to illuminate universal processes. If you're trying to explain things globally everywhere in the world, you're forced to think more about fundamental processes than if you're just explaining local features. Also, the ocean and global society are both connected throughout the world, and they interact at global scales. So whenever you're thinking only locally, you're missing things that are happening in the rest of the world that will then impact your local space. And finally, both climate and the oceans require global policy. So I think a global perspective is essential, even if it's very challenging. And then why models? Why should we use models at the global scale? So, I mean, I think I could say many reasons for this. For me, one of the most important things is that there is so much stuff happening. I mean, we've heard about many things that are happening in the ocean during this week. Alistair gave us a sense of how urgent things are, given the rapidity of changes and the multiple kinds of changes that are happening in the ocean. And it can be very overwhelming. So I find that models are great as synthesis tools, because you can include different processes, you can play them off against each other, and this helps you see which ones are the most important, which ones are the most poorly understood, and which ones can potentially take us in the directions of solutions. So really, what the heck is happening and what might happen in the long-term future are things that we can really try to think about quantitatively with models. Okay, so there are many different modeling approaches that one could take. The one that I'm going to talk about today is what I would call the climate model approach. And so this is really a way of thinking about the global system that was pioneered by climate models, which have now been renamed as Earth system models. And the idea is you take the surface of the planet and you divide it up into a bunch of discrete boxes. Inside each one of those boxes, you have state variables that describe the current state of what's happening inside that unit. And then you have equations that describe how those state variables change over time. And so this is what's used through the IPCC process for climate projections. So there's a few important things about this approach. One is that it strives to be grounded in general principles so that you use the same equations in all the grid cells. You treat everywhere on equal footing. It resolves space and time. So it resolves space by including the two-dimensional or three-dimensional aspects of the Earth, and also they evolve through time. And so far, they've been widely used for biogeochemistry in the ocean, so including plankton and their interactions with the chemistry within the same framework as the ocean physics. And the other nice thing about the climate models is they can produce beautiful movies that you can just sit and stare at for hours if you have the time, watching the little whirls that appear. But we're concerned here with what's happening across the whole system. I mean, I think this is something I really like about the IMBeR community, is that it's trying to understand the full system, going right up to what's now named the blue economies, so the human interactions with the system. So we've got to go from these climate biogeochemical models, which are mostly at the global scale, across to what's happening at the blue economy. And this requires bridging across ecosystems as well as humans themselves, what they're doing. And there's lots of work on modeling ecosystems in many different ways and many different environments, most of which have been local. So there haven't been many attempts to do general global models of ecosystems in the same way that there have been of biogeochemistry. And for humans, there's very little in terms of general global modeling and a real diversity of approaches in what's been taken there. So I think there's a lot of work to do in linking across these scales in order to see what's happening. So I think this is important. So one recent piece of progress in this direction I'd like to highlight is the Fisheries and Marine Ecosystem Model Intercomparison Project, FishMap. So this is included efforts from many, many people, but I'd just like to highlight the people who have really pushed this forward: Heike Lotze, Derek Tittenser, and Tyler Eddy, who's here. And FishMap has been successful in bringing together a wide diversity of models addressing the marine ecosystem. So these include regional models, EcoPath with EcoSim, Atlantis, Osmos. Maybe you've heard of these. They've been very widely applied. But it also includes some newer global ecosystem models listed out there on the right. And so it's bringing all these models together, really following in the footsteps of the Climate Model Intercomparison Project, CMIP, which has been around for much longer, which has, fancy graphics like this showing their simulation protocols and fancy websites with maps showing where all of their 80 participating models come from. So this has been around for decades, been hugely successful, very important in the IPCC process. But really the key is that they define standardized simulations and output formats so that all of the participating models run the same experiments, so you could really properly compare between the different models, because they all behave different ways, they're all built by different people with different assumptions. And very important, although very boring sounding, they have common output formats so that you can easily compare them. And getting to that point with fish models was actually very difficult. So it's a non-trivial thing, actually, organizing all of this. It's a lot of work. But so that's the idea. And I think an important FishMap paper just came out last week. First author is Heike Lotze, just came out in PNAS. And this shows these standardized responses of these global upper trophic level ecosystem models to climate model, biogeochemical model forcings. So this is showing from that paper a range of the upper trophic level model responses to two different climate model, biogeochemical model forcing sets. And what you can see from this is there's a range of responses between the different models. And I won't get into the details of any of that. This is the percent change in the global biomass in each one of these models. So these would be positive relative to this 1990s baseline, and then these are decreases up to 40% in the simulated biomass at the bottom here in these different ecosystem models, going through to year 2100 under RCP 8.5. So that's the worst case scenario climate change radiative simulation. And so there's a big spread. There's a lot of differences in how sensitive these models are to this radiative forcing, but I would like to point out that none of them go up. So we didn't know this going in. There's ways that if there's more primary production, things can go up, and they depend on temperature, spatially, so they could have gone up, but none of them go up. So even with very different assumptions and constructions, all of these models project a decline in global biomass, to some degree, except for this one, but it doesn't go up. And what was very encouraging was that earlier this year, actually, the first global assessment of temperature sensitivities in historical stock assessments was published. So that's shown here in this gray line with this wiggly uncertainty window here. So we were able to compare the stock assessment-based estimate of change from 1970 to 2005, this historical period, to the ensemble mean. So this is the average of that spread of models that I showed. And it was very surprising to see that it actually agrees extremely well with an uncertainty with the trend, as published in Free earlier this year in Science. So the ensemble average is consistent with the assessed stocks in showing a magnitude of decline of something like 5% per degree Celsius of global surface air temperature change. And I think I've heard something like this before, I don't know where from, but to paraphrase from George Box's famous saying, all models are wrong, but the multi-model mean is maybe not so bad. So it seems like, similar to things people have observed with climate models, it may be that by averaging these models together, we get something that's better than, that the sum is better than its parts. So, okay, so this is taking the coupled climate biogeochemical model output and then feeding that into upper trophic level models, which I call offline because they're not interacting. So this approach is great, it's a step forward, but it's not including the effect of upper trophic levels on lower trophic levels and biogeochemistry, which of course is something that many people here are interested in. So, how can we address that? What can we do to build a whole ecosystem strategy? I mean, I haven't seen this applied at the global scale, but I think if it has been, I think we still need more work in this direction. But of course, it's very difficult because we know that there's a huge diversity of species at the global scale, especially when you're thinking across the whole ecosystem. It's kind of overwhelming. Most marine ecosystems are poorly observed, so we have limited data that we can use to constrain models, which makes it very difficult. But I think as a result of these features, we need something that's general. And yet, if it's going to resolve changes over time, it needs to have a mechanistic basis. So we need a general approach that is still closely linked to mechanisms of change. So I've become convinced from the work of, a lot of great work in the field of size spectra, that body size is really the master variable that we should be focusing on for thinking about the whole ecosystem. How many people agree right away? How many people do I not need to convince that the size spectrum approach is awesome? Just a couple people waving vigorously, everybody else not so sure. Okay, good. So let me convince the rest of you that you should be waving vigorously too. So first, body size varies in the ocean by a huge range, over a huge, huge range. It goes, so this is in body mass, so the mass, the size of individual bodies on log base 10 scale. So bacteria are down here, 10 to the minus 13 or 14, and whales are up here at 10 to the 8. So this is an enormous range in body sizes across here that we can think about. One first off thing about the size spectrum is that it separates out the part of the ecosystem that we care most about. Really, when we're talking about blue economies, when we're talking about things that people on the street care about, it's really the beautiful and delicious large things over here at this end of the spectrum. Oh, someone was offended by that. Is there a marine microbial ecologist who's in control of the screen somehow? Okay. Oh, wait, squeeze back. Oops. It's so, this computer system was blown away by the awesomeness of the size spectrum. Okay. Okay, and right, so there's been a lot of work really on the size spectrum going back almost 100 years really on how important body size is. I'm not going to try to review that. There have been some great reviews over the last few years. I just highlight one by Julia Blanchard and one by Jérôme Guillet, and also by Ken Anderson. Ken Anderson had a great review in Annual Reviews of Marine Science with this awesome image where he shows over that huge range of body sizes how fundamental features of how life operates can be directly related to their body size, just through physical constraints on things like body temperature, resource encounter strategy, life history strategy. So there's many functional connections to body size. And you can think about this if you think about a tuna, for example. So a tuna, when it hatches, has a size, that you would measure with milligrams, and over its life, it grows into something that can be 100 kilograms. So it's passing over like 8 orders of magnitude in mass over its lifetime. And as it does so, it's going from the viscous regime to being an animal that can swim across ocean basins, and it's changing trophic relationships, and it's changing metabolic rates. Everything about it is changing so that it has much more to do with zooplankton when it's this size than it does to do with its adult self. So for many reasons, size in the ocean is really a great way to describe organisms that can be much better than the species level description in many cases. So that's one thing. Another thing is that it shows very regular patterns. So we know there's all this diversity and we can get overwhelmed by the complexity in the ecosystem. But when you look at things versus body size, standing back and looking over the whole spectrum, you see some remarkably regular patterns. So this is from a paper of Ian Hatton's, but this is showing the maximum growth rate. This is now not even just the ocean. This is all life, all eukaryotic life. What you see is that growth rates, so these are the growth rates per organism, scale very regularly. I mean, so there's at least an order of magnitude variability here, but when you stand back and look, it's very regular across all life. So this is really hinting at universal processes, universal mechanisms that can inform size-based models. And there's another universal feature of size spectra that was suggested by Sheldon. How many people have heard of the Sheldon spectrum, Sheldon abundance spectrum? Okay, so more people for that, but still not everybody. So this is a remarkable suggestion made in 1972 by Ray Sheldon and colleagues working at the Bedford Institute in Halifax in Canada. And they went out with some of the first Coulter counter cruises to widely sample in the ocean. And they found, messy distributions, but when they traveled around, they didn't see any systematic trends in the distributions. And this is a summary of their view of things from both work in the equatorial Pacific and in the Antarctic, where they suggested that the biomass, so this is the concentration of biomass in these regions compared to the body size on a logarithmic scale. And they suggested when you add up the biomass on a logarithmic scale, that basically, to a first approximation, there are roughly equal concentrations of material at all particle sizes within the range from bacteria to whales. I mean, that's a remarkable statement that they really made based on very little. But it's prompted a lot of speculation. It's been the impetus for a lot of size spectrum models to be built. But as far as I know, it hasn't been rigorously tested with global data. If anybody knows, please let me know after this. But Ryan Hennigan and Ian Hatton and I have been talking about this quite a lot and getting excited about it. And we thought we'd try just taking a shot at estimating what the pristine global size abundance spectrum might have looked like from global data, because now we have a lot more data available than Sheldon did, and we can try to add these things up at a global scale. So I'll show you this is just preliminary results actually, really. But for the phytoplankton and zooplankton, I'll use satellite observation-based algorithms, and then I'll use data-constrained global models for the fish biomass that have been corrected for the loss due to fishing, and then similarly for whales. So using historical catches, population models, and as informed a little bit by the genetic studies. So when we put those things together on the size spectrum plot, so where this over here, so this is the total mass per logarithmic size bin in petagrams, that's equal to gigatons of carbon on this axis. What do you think it's going to look like? Drum roll. Here it is. Pretty flattish. So these are showing ranges where you have ranges available for phytoplankton estimates from different algorithms and different satellite products. Here's different ranges from fish biomass, from very different fish biomass estimates. So there's plenty of room here for wiggling. But it's remarkable that the means here agree quite well, the means of these estimates. And it's not inconsistent with what Sheldon suggested, although the whales seem to be quite lower. So these are really pretty high bounds for pre-whaling whale populations. So it seems like this is low. So it doesn't seem like it's completely flat all the way to whales, but you could very speculatively just take your thick black marker and draw a couple lines through here maybe something like this if you just go through the middle. So maybe there's a bit less phytoplankton, a bit more of these, and it clearly drops off to 0 here because nothing is larger than a blue whale. Or it could be a hardcore Sheldon interpretation where for some reasons that we don't understand, it's absolutely flat across the spectrum. I think it's remarkable that we don't know the answers to these questions about how this works, and I think this is something we need to figure out. But something we can use this to illustrate right away, because we took this from estimates that include fishing effects on the fish biomass and the effects of whaling on this biomass, is we can just sketch in roughly what the impacts of fishing and whaling were on the global size spectrum, and just approximately looks something like this. So this is, I think, more or less what we've done to the global biomass size spectrum through fishing and whaling. We don't have constraints, so who knows if there were ripple effects down here or what that's done to the rest of it, but that seems to be about what we've done at that end of the spectrum, which is unfortunately the beautiful and delicious end of the spectrum that we care about. So, the global size spectrum. So the available data, sketchy, large uncertainties, but they're consistent with the Sheldon hypothesis for a flattish overall biomass distribution with about 1 petagram of carbon per order of magnitude size bin all the way across the spectrum. It's remarkable. Fishing and whaling have definitely altered the shape. We can use this to then construct some hypothetical ecosystem responses to change, as we talk about in a paper led by Ryan Hennigan, just came out recently. And this should be an excellent foundation for building a unified ecosystem model. So I think this is work to be done that could be very exciting. So for the rest of the talk, I'm going to shift into talking about humans and linking humans into this ocean, really where they're interacting up at the large end of the spectrum. We're very large animals compared to the rest of the animals around. We're up here. And we interact with things of similar sizes to us, mostly by killing them and pulling them out of the ocean. But so now we're going to talk about trying to resolve those things at the global scale. So the goals of this part of the work are to really try to get a climate timescale understanding of the global industrial fishery. So by that I mean trying to understand what controls it on a 50 or 100-year timescale. And also considering human well-being, as I will at the end. And for the first part here, I'm going to talk about a particular global model. So this is one of the participants in FishMap, the boats model, which is a size spectrum model, but it just resolves this part of the spectrum. So it's just the fishing part of the spectrum, and then the fishing boats that go along with it. So I'm not going to try to, I'm not going to try to explain the model because it's complicated, but I'd love to talk about it with anybody who would like to. But it's a coupled environment, ecosystem, economic model. Instead, I'm just going to show you some results. And these are detailed in this paper that came out a couple of years ago, and Kim Scherer, who's here, is now working a lot with pushing this forward with new scenarios, new projections. So this plot is showing the global history of wild capture fish harvest in millions of tons. So up to 150 million tons here. And the black and gray lines are showing 2 alternate reconstructions of the global wild capture harvest with this strong increase and then a plateau or maybe a slight decline since the 1990s. The other 2 lines here, the blue and the gray, are showing 2 model simulations with the boats model where we've done hindcasts. And so we've looked at various economic forcings and environmental forcings in this previously published paper. But the thing that really jumps out as being the only thing capable of driving this strong increase when you look at the various forcings available is technology. So this has to have been driven, this big increase in fish harvest has to have been driven by increasing skill of fisheries to go out in the ocean and exploit new stocks, spatially expand, and grow the catch that way. And this shouldn't be surprising if we think about what fishing boats looked like in 1934 compared to what fishing boats look like today. Of course it's technology, right? So this had to play a huge role in the 20th century wild capture fishery. So then we can take this model, which has been tested against the historical global fish catch, and try to see what it thinks will happen in the future. So running future scenarios. And here, these are just very simple scenarios, so no complicated narratives, just some idealized scenarios. And for the environmental changes, we can take climate model output. So here I'll just show a stabilizing case and a rapid warming RCP 8.5 case, and compare those, so for the price and the cost per unit effort, we'll hold those constant, and then increase the catchability over the 20th century to simulate continued increase in technological skill, assuming that it continues to increase as people continue to innovate. And then this is also going to include regulation from some work that Kim's been doing, allowing various strengths of regulation effectiveness. And so I'm going to show a case with absolutely no regulation. So imagine total breakdown of society. Everything is open access, fish as you will, compared to very strong maximum sustainable yield targeting regulation at the global scale, just to put the upper and lower bounds on what could be feasible. And I'll just show you quickly here what Kim finds for that subset of the scenarios that she's run. So she finds that if we continue technological progress with no regulation, the model suggests that the global harvest will decline as serial overexploitation of resources expands throughout the parts of the oceans that haven't yet been overexploited, and everywhere goes into a decline. Bad news. But in contrast, if regulation is perfectly effective and targeted towards maximum sustainable yield, the model thinks that it should be possible to maintain high regulations, and this is accounting for reverberations in population dynamics around the world coming out of the historical transient, and also climate change. So this one here, the relatively level blue one, also includes the climate change RCP 8.5 scenario. The dashed line up here is including climate mitigation. So this shows what the model thinks would be the MSY if climate stabilizes. So this is the effect of climate in between these two. So just to try to summarize that, if we try to think about it in terms of an MSY shortfall, I'm not advocating for MSY here. We're just taking MSY as an illustrative target. But if we try to think about this as the shortfall below what we could have due to these different factors, it suggests that, according to the simple model, and this is just a schematic illustration, I would say, but I think the dynamics are interesting to think about. In 2020, the lack of perfect regulation would be responsible for a shortfall in MSY, something like this, something like 30 million, 20 million tons, something like that. And climate is not very important, but then moving forward to 2050, climate has become much more important, and the effect of regulations has become far more important. So I think the take-home point from this is that regulation is becoming increasingly important and can counteract climate change losses. So I think everybody who's working on regulation here, thank you. I think it's extremely important work. It's the most important work to be done in preserving wild capture fisheries, I think. At least that's what the model makes it look like. Okay, so that work is looking at long-range fishing within this global Earth system model perspective. So on all these grid cells out here, the dark blue ones in the open ocean, those are profit-driven fisheries that are heading out to capture wild fish. But of course, we know that there's a lot of communities, actually far more people depend on short-range fisheries in coastal regions, especially in lower-income countries in the world. And these are not as often thought about in theoretical models as we're looking, because they're not profit-driven. So something else that we really wanted to do here was try to think about how to include these people. And, as Eddie was talking about the other day, we should really be thinking broadly about equity and non-monetary benefits that are being gained from the ocean. So we're trying to think about ways to bring that into the same kind of framework. And so one approach we're taking to this is asking people questions. I'd like to ask you this question. So, all things considered, how satisfied are you with your life as a whole these days? Use a 0 to 10 scale where 0 is dissatisfied and 10 is satisfied. Everybody got an answer? It doesn't take long, eh? I mean, why is that? I don't know why people can answer this question so quickly. Like, nobody ever sits down and calculates this, and everybody's just kind of like, oh yeah, this is my answer. People are quite confident. This question, and questions very similar to this, have been asked millions of times to millions of people. And it's fascinating how consistent people are and how they answer this question and how it's consistent across societies. And anyway, it's a fascinating field of work, the field of subjective well-being. And this is a particular kind of subjective well-being, this question. This is a cognitive life evaluation or a subjective life evaluation. But it's something that's been used a lot by economists, and many people have proposed this as a way to quantify, benefits for humans that's non-monetary, as a nice alternative. So there's been a lot of work on this question, so I think it's really interesting. And it's been shown that at the global scale, this question and questions like it are answered on average with something between 5 and 6. So you can compare your answer to the global average and see how you're doing. But that's the global average. I think to this exact question, it's about 5.5. So Sarah Mignaro, who's here and will be talking about this afternoon, has traveled to two very different countries to visit small-scale fishing communities to ask them this question, along with a number of other questions, in order to try to understand their well-being in ways that can be quantified and therefore that we can bring into the model framework. And this is very early days for this, so I just want to give you a hint of her kind of preliminary results. But the communities, that was supposed to appear after. I just gave you the conclusion. Anyway, the communities here are Bangladesh, a couple of communities in different parts of Bangladesh and in different parts of the Solomon Islands. And so they have different kinds of fishing. Here in Bangladesh, it's more market-oriented fishing. In the Solomon Islands, it's very subsistence fishing. People are just fishing for their own daily meals. And basically, the findings that Sarah has so far is in the answers to the satisfaction with life question in Bangladesh are an average of 6.7 on that scale of 0 to 10, which is significantly higher than the global mean and significantly higher than the countrywide reported average for Bangladesh in the literature, which is only 4.5. So we think that's interesting. And it's also, unfortunately, there's no countrywide data available for the Solomon Islands. The Gallup World Poll that does the global surveys hasn't asked the question there. But in the fishing communities that Sarah visited, she found extremely high answers of satisfaction with life, which also fit with other measures of their well-being, like their affect. Very, very high, 8.1. So this is as high as people answer in the wealthiest industrialized countries of Northern Europe, which are usually at the top of the global rankings for satisfaction with life. So, I mean, this is just the answer to a question. So as like a natural science background person, I find it difficult to interpret these numbers. It's just how people are answering questions of words. But I think it's very intriguing that these seem to be among the highest values in the world for what are materially some of the lowest income societies. I mean, some of these places don't even use money. So I think that's very intriguing, and we should do more work in that direction. So to summarize, hopefully I've convinced you that global predictive models are important in that they can provide context, they can help with process understanding, they can fill gaps on the map, and they can illustrate possible futures for the human ocean system. The existing global fish models in the FishMap intercomparison unanimously predict a decrease of fish biomass due to climate change in the 21st century, which has an average decline of roughly 5% per degree Celsius. The size spectrum, I think, offers a uniquely powerful and tractable approach to the entire marine ecosystem. I think that's very promising, and it's consistent with the Sheldon abundance distribution. Direct global coupling of humans and ecosystem can help to understand the dynamics of the blue economy. I think there's much more work that can be done in that direction through direct coupling. And I think there's great potential to build integrative, quantitative, non-monetary measures that are of human relevance, such as well-being. I think there's many others that you could include as well, and include these in global models. So thanks very much for your attention.
So thank you, Eric, for a wonderful talk, and the floor is open for questions.
Thank you very much for your presentation. My name is Aliou Sall. I'm coming from Senegal. I'm a socioanthropologist. So I have some questions, just two questions, briefly. While talking about self-evaluation, subjective self-evaluation of life, of someone's life, you have been giving some example on regarding some studies or some survey you did in fisheries. So I've got a little bit confused because in my mind, maybe I'm referring to my local context, fisheries is a part of a whole social system. So in the way this is presented, I realize that there is, on one hand, the evaluation, someone's self-evaluation of life, to what extent he's satisfied with the way he's living. And on the other hand, there is something quite different, that is job satisfaction, These two are to be distinguished in my way of understanding. I don't know what you think about.
I completely agree. No, thank you very much for that question. I totally agree, and that's actually what Sarah is finding in the more detailed analysis of her data. So she'll be speaking about this afternoon, if you want to talk to her. But it really seems to us like the thing that jumps out is the difference between communities. So you see that, because she's asked these questions to fishers as well as non-fishers, and there's no significant difference between the happiness of the fishers and the happiness of the non-fishers. It's the community. So really what this is showing is that these subsistence, I think, the subsistence communities in the Solomon Islands in particular, they're just very happy communities. They're very satisfied with their lives. But it's the whole community. It's really not the direct fishing activity itself that seems to be the most important.
Okay, thank you very much, man.
Okay, thank you.
Yeah, we have time for one or two quick questions from the audience. Oh, there's one in there.
Hi, Eric. That was a really interesting, thought-provoking topic, and I saw yesterday you were very excited about your size spectrum, so I wanted to make a comment about that actually you got me even more excited than your plot about it. So I wanted to ask you, you had the whales on, but you've left off sort of the rest of the marine mammals like the seals, which are also large body mass and sort of occupy that similar role in many ways. So I was just wondering if you could get the data to add them in. I think that would push that sort of marine mammal category up a little bit because they're sort of closing that whole ecosystem. But my question to you was to take it even a bit further. It occurred to me that what's missing on the plot is us humans that you were talking about trying to embed in all these models. And if you could easily work out the biomass of humans at any one time that is actually sort of preying on ocean food, because we know what food consumption is. You could work out, what's the biomass of humans, and you could put us on that plot, and it would be really interesting to see if we sort of fit the pattern or we totally throw it out. So there's a challenge. I don't know if you have a feeling for how that might look, but I'd love to see that.
Thank you for those great questions. So for the seals and other mammals and big sharks and things, it would be great to do it. So just haven't done it. So, but because I don't know exactly where to work. So the whales are easy, especially the great whales, because they're big. There's not very many of them. There's only like 12 species of great whales. They cover a couple orders of magnitude, and they don't overlap with anything else. So that's easy. So that's just why I did that. But I agree. I think there's so much we could do with the size abundance spectrum just in digging through existing data. I think there's a huge potential to really take this much further. I think because it's so important mechanistically, it's such a great way to model the system, such a great way to see the whole interactions everywhere, that it would be great to have some data compilation efforts and ways to bring new observations so that it's automatically formatted properly so that people can really look at the whole size abundance spectrum globally more easily. And then, wait for the second part. So Daniele Bianchi calculated the total human biomass. It's not very hard, but it's about half a petagram. So about half of the marine ecosystem average for a whole order of magnitude biomass. So just to give you a sense of how many humans there are, there's a lot of humans, but we only get about 1% of our food from the ocean. So I don't know if that means you multiply that by, you divide that by 100. But super interesting. Yeah, thanks, Siva.
Yeah, so we're running out of time. Thank you again for engaging talk.
Okay, thank you everyone.